Okay, so this is the week 6 free response solution for the rotational velocity, or no, wow, rotational kinetic energy and rotational momentum week. All right, so this is a 7-point problem. Suggested time is 13 minutes. So it looks like we have a wooden wheel of mass m consisting of a rim with spokes rolling down an incline that makes an angle of theta with the horizontal as shown above. The ramp exerts a static force of friction so that the wheel rolls without slipping. Okay, so right away, some things that I know the question might ask about. The question might ask about energy conservation. Okay, and it says that the wheel is rolling. So in this case, we have gravitational potential energy converting to translational or linear kinetic energy and rotational kinetic energy. So that's one thing that I might be asked about. Another thing that I might be asked about is forces and torque. Okay, so I might need to look at a net force equation going down the incline and a net torque equation, okay, for the object rolling that way. Okay, since this is rolling, there must be a net torque. And just as a reminder, when you have something rolling down a surface like that, the torque comes from the force of friction. Okay. All right. So let's look at the first question. We have on the diagram below, draw and label forces. So forces, not components, not torque, that act on the wheel as it rolls down the ramp. To clearly indicate which point on the wheel the force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. So if the force is exerted between the surface and the wheel, the force should start at the wheel. The lengths of the arrows do not need to indicate relative magnitude. Okay, so right away I know there's going to be a force of gravity, and we're on a surface, so there's going to be a normal force. We've already talked about a static friction force, so I also need a static friction force. Okay, so now I just need to figure out where those forces are acting. Okay, force of gravity always acts at the center and points straight down. So I'm going to start from the center dot and draw a line straight down. Okay. The normal force is a force between the surface and object. So that means my normal force should start at the surface. Now remember, normal force means perpendicular to. So my normal force should kind of start at the surface here and move upwards like that, okay, perpendicular to the surface. And then last but not least, the force of friction, also between the surface and object. Okay, so this wheel is rolling this way, and I know that friction creates the torque that allows that to roll. So that tells me that friction needs to point up the incline like so. Okay, so I have drawn all my forces, I have labeled all my forces, I've pointed them out where the force is exerted. Okay, so as the wheel rolls down, which force causes the change in angular velocity of the wheel with respect to center of mass? So change in angular velocity means an acceleration, which are caused by torques. And with respect to the center of mass, so that just means that that is our axis of rotation. Okay, so the force that is creating that torque we've already talked about is the force of static friction. Okay, why? Friction is the only force at a distance from the center of mass and perpendicular to lever arm. So it creates a torque which leads to a change in angular velocity. Okay. So I talked about which force, the force of friction with respect to the center of mass, and I briefly explained my reasoning. So I went through why friction creates a torque and torque leading to change in angular velocity. Let's go ahead and check my points for that first part. I feel like I'm going to sneeze. So if I randomly sneeze in the next few minutes, I'm sorry. Okay, so question A is 2 points. So I get 1 point for a labeled arrow representing gravitational force starting at the wheel center and directed downwards. I definitely did that. And I get labeled arrows representing friction and normal force, or a single arrow representing the resultant of the friction and normal force, i.e. a force exerted on the wheel by the surface with no extraneous forces. So I did that. So that resultant force that they're talking about, since both of the friction and the normal force are created by the surface, you could combine them into one force that looks something like that. But that's not really anything we talk about, and that kind of confuses a lot of people. But that's what they're referencing in that part. Okay. Oh, and then I gotta do B2. B2 is 1 point, so I get no points for saying the friction point. So correctly explaining that friction is the only force that exerts a torque with respect to the wheel center of mass. I did that. So their example is the point is also earned for casual chain reasoning of forces. Gravitational force leads to the normal force and acceleration down the ramp, which leads to friction, which exerts a torque. That's a strange way of thinking about it, but you could also do it that way. All right, so now let's do part B. So for this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. So remember, static friction can increase up until some maximum point, and then it drops away. We usually focus on this maximum point, but this question is referencing this point in here. So we're not at that maximum value yet. Excuse me. So instead, the magnitude of the force exerted on the wheel is 40% of the magnitude of the force or force component directed opposite the force of friction. Okay, so the force directed opposite the force of friction is the force pointing down the incline, since friction points up the incline. Well, what points down the incline? Fg sine points down the incline, which means that my friction force is 40% of that Fg sine component. So we need to derive an expression for the linear acceleration of the wheel in terms of m theta and physical constants. So that could be baby g. So linear acceleration, I don't have any distances or times or velocities, so that tells me I need to look at a net force equation, specifically a net force down the incline or parallel to the incline. Okay, so if I was to draw this free body diagram as a true free body diagram without worrying about where the forces are acting, okay, I would have Fg pointing down, Ff pointing up the incline, and a normal force like that. But remember, Fg gets broken into components. Okay, specifically, Fg gets broken up into Fg parallel or Fgx, which is the same as Fg sine. And it gets broken up into Fg perpendicular, which is Fg cosine. Okay, remember, Fg perpendicular and the normal forces are opposite of each other on inclines. And friction and Fg sine theta fight each other. So we're focusing in on this direction here. Okay, so just those two forces. We can ignore Fg perpendicular and the normal force. Since Fg sine theta points down the incline, and that's my direction of travel, I'm going to call that the positive force. So Fg sine theta minus the friction force is ma. But it tells me in the problem that the friction force is 40% of that Fg sine theta. Well, how am I going to represent that in equation form? Remember, all percents can be written as decimals. You just divide the percent by 100. MA. So I have 1 FG sine theta minus 0.4 FG sine theta, which gives me 0.6 FG sine theta. Now, incorrectly, a lot of students will stop here, forgetting that they can only have M, theta, and G. FG is not an allowed variable, so we have to turn that into MG sine theta, which then shows us that the masses cancel, and we're left with 0.6 G sine theta is the acceleration. So let's check my points on that. That was for B. So I get an expression, a point for the expression for the sum of the force components parallel to the ramp that recognizes that there are 2 forces. So basically for my net force equation. For indicating that the friction force is 0.4 mg sine theta, and correctly solving for the acceleration in terms of correct variables. So that's that. And I get that second point. Yay! All right. So, problem C. In a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at a time. At the same instant, the wheel is released from rest. So 2 things released from the same height at the same time. The block slides down the ramp with negligible friction. Okay. Which object, if either, reaches the bottom of the ramp with the greatest speed? So greatest speed. All right. And I have to explain my reasoning in terms of forces. So I'm going to think about right away the forces acting on the block of ice as compared to the forces acting on the wheel. And I'm going to draw a simplified free body diagram since it's not asking about anything rotating quite yet. So here's my wheel. Here's my ice. Okay. The big difference between the wheel and the block of ice is that the wheel has that up the incline component of friction, whereas ice does not. Okay, so if I was to write out my net force equation for the parallel direction, the wheel would look like Fg sine theta minus the force of friction is MA, whereas for the ice, it would just look like MA, or Fg sine theta, is MA. So what this tells me is that the ice is going to have a larger acceleration because it has a larger net force, which means that it's going to, over the same distance, reach a faster velocity. Okay, so which one reaches the greatest speed? I'm going to say the block. And I'm going to write my reasoning down here. So the block has a faster speed because without the force of friction, the block has a larger net force, therefore a larger acceleration, which over the same distance, because the ramps are the same distance, will lead to a larger velocity. Done. Okay, cool. That's okay. So now I have to explain my answer again, but now in terms of energy. Oh boy. Okay. So let me draw 2 wheel. Okay. And this is ice. Okay. So both are at the same level. So what does it tell us? Okay, it also has a mass m. Okay, so we're at the same height. We have the same mass m. So we start with the same gravitational potential energy. Okay. Now, energy is conserved. Okay, but it's conserved differently in each of these two examples. If you remember, in the beginning of the problem, I said that the wheel converts its gravitational potential energy into translational kinetic energy and rotational kinetic energy. Whereas this block of ice, all of that initial gravitational potential energy is going to turn into linear or translational kinetic energy. Okay, so that means that the ice has more kinetic energy, which is going to lead to more velocity. So that's essentially what I need to explain. So here, both objects start with the same amount of energy. Energy is conserved in both. However, the wheel has rotational kinetic energy and linear kinetic energy at the bottom of the hill. Okay. Less linear kinetic energy compared to ice yields less linear velocity. So I actually explained that a little bit opposite of what I was originally going to do. So I explained why the wheel has less instead of why the ice has more. Either way is fine. Either way would be correct. You could say that the ice block converts all of its initial energy to linear energy, whereas the wheel must split its energy, and that means that the ice has more energy in linear kinetic energy, so it has more velocity. That would be fine. I just happened to do it opposite of that. Okay, so let's check my points and make sure I got all my points. How fun. Both of those explanations were only worth 1 point. Okay, so I get a point for a correct explanation in terms of forces. For example, the wheel experiences a counteracting friction force, so the block has a greater net force exerted and therefore greater acceleration. I said basically exactly that. So the second part of C, for a correct explanation in terms of energy conservation, okay, so both object Earth systems lose the same amount of potential energy and therefore gain the same amount of kinetic energy. With the ice block, but not the wheel, all the kinetic energy is translational and none is rotational, so the block is faster. I essentially said that. I just didn't talk about this part, but I did talk about energy conservation, which is essentially what this statement is referencing. Okay. So that is the answer to this week 6 question. Hope you have a great day.